Recording has started. Give it probably a couple more minutes just for any stragglers. Okay, 5:04. Let's give it till 5:05. Just a little.
How is everyone doing?
Yeah, everyone happy to be done with the semester?
I'm very happy.
Still got finals left, but...
Did it work well, or did you find it was a disaster?
I was actually surprised at how well everything worked. The lab was definitely the most interesting. They had to mail us kits to build circuits and stuff.
I have that next term. They're gonna make us go pick it up and do it at home.
Okay. 5:06 actually. I guess we should just get started, and then anyone who shows up later, I mean, it's recorded. They can see the earlier part if they want to. Okay. Screen sharing should be enabled, so...
Okay, is that good? Can you see that?
Yep.
Yep.
Okay, thanks, Eleanor. I'll begin. We decided maybe if you have an urgent question, you could jump in and ask it. Otherwise, let's wait till the end. But if you really want to ask a question during the middle, that's fine. I'm fine with that. Okay, so what I wanted to chat about with you today is a project that we've been working on for several years now at UBC. And there's a bunch of names at the bottom, and I think you might recognize a few of them because some of them are your undergraduate colleagues. Everybody in orange there is or was an undergraduate at UBC, and they've been involved in this project. And by tomorrow, we are submitting a very big paper, which is what I'm discussing today. And a large number of undergraduates have really played a very important part in this. So one is Stephanie Grondin, who you might know. I think she was the president of the Astronomy Club a few years ago. Is that a name we know? No? She's now at Toronto, first year in graduate school. James Hegarty is still an undergrad here. I think he's in fourth year now. Ronan Kerr is off at Texas as a graduate student. Dave Miller is a graduate student here now, and Sarah Teal is, I think, graduating this year. She's also an undergraduate student. So this is also a little bit of a selling point because we really like to hire undergraduates as summer students and so on, and they do a fantastic job at this. And you get your name on a paper, which is always a good thing if you're eventually going to apply to graduate school. So that's a little bit of a selling point. Okay, so this is a picture of a star cluster. It doesn't look like very much of a star cluster because it's a sort of wimpy thing, but I'll show you a blow up of one of the most interesting stars in this picture, which you may or may not be able to see at the moment, but I'll blow it up in a little bit later in the talk and you'll see it. So what I want to do today is talk about, let me just change this a little bit. Okay. What I want to do is talk about several aspects of things that we've been working on. And wait, I want to just try and get this in here. Okay, we'll leave it at that. Okay, so two of the big questions in astronomy that we've been thinking about, which I just want to keep in the back of your mind this whole talk, is it involves supernovae and white dwarf stars. So one of the questions is, what's the lowest mass star that can make a supernova? People think it's about 8 solar masses, but you're going to see that what we do today is going to have some impact on that. And sort of the related question is, what's the maximum mass of a white dwarf star? And people think the current answer is thought to be about just under 1.4 times the mass of the sun. And if you're not sure what a white dwarf is, I will tell you in just a couple of minutes. Okay, so let me spend a few minutes talking about white dwarfs. So these are objects which are typically small stars. They're about the size of the Earth, but they're about half the mass of the sun. So I just want you to imagine taking something the mass of the sun and putting it into the size of the Earth. So you can anticipate that this thing is going to be incredibly dense. And what we're talking about here is something like 100,000 to 1,000,000 times the density of water in a white dwarf. So this is an incredibly dense star and pretty small. It's about the size of the Earth. And the picture on the right shows an image of a real white dwarf. This is a Hubble image that was taken some number of years ago of Sirius A and Sirius B. So Sirius A, I'm sure you can see with your naked eye. I'm sure most of you have gone out and seen it. And if you haven't, you should go out tonight and see it because it's clear out and you can see this quite easily. So Sirius A is just a regular normal star, about 10,000 degrees. And Sirius B is its companion, and Sirius B is a white dwarf. Now, what looks like Sirius A being much bigger in this picture is not really correct. That's just scattered light in the optics. But what you can get out of this and what is accurate is the relative brightness of the two objects. So you can see that Sirius A is incredibly much brighter than Sirius B. And interestingly, they're both about the same temperature. So it's not a temperature effect, but it's a size effect. Sirius A is just way bigger than Sirius B. And it just shows you how small a white dwarf is and how little energy you get out from a white dwarf because they're so tiny. Now, what in fact are white dwarfs and where do they come from? So this is what's called a Hertzsprung-Russell diagram. I don't know if you've seen this before, but this is a plot of the luminosity on the y-axis increasing upward, the luminosity of a star versus the temperature of a star on the x-axis increasing toward the left. And there's a line here called the main sequence, and that's where most of the stars in the universe sit. And this is where a star sits in a diagram like this if they're very quiescently burning hydrogen to helium in their core and just not doing very much. And our sun is doing this. Our sun is sitting right about here on this diagram. And the sun has been there for 5 billion years, and it will be there for another 5 billion years before it exhausts its central hydrogen. It gets converted to helium. When that happens, the star evolves in this diagram, and it goes up the red giant branch, which is this branch over here, and it goes to really to very much higher luminosity. It goes up more than 10,000 times brighter than it is now. And of course, when the sun does that, it's going to wipe out the Earth and all the planets. So we only got about 5 billion years left. So start planning. At the tip of the giant branch up over here, helium starts to burn in the center of the star, and the star moves off over here in the diagram. And when helium is completed, it goes up the giant branch a second time. It ejects its envelope. It exposes the core, which becomes the white dwarf star. So this is just, I'll show you in a moment what the core really, what the core really looks like. And it slowly cools along a track that looks like this. So this is what a white dwarf looks like as it's getting rid of its outer atmosphere. So this shell that you see here, this is not like a donut, by the way. This is a shell, and it just looks more dense around the edge because you're just looking through more material around the edge. So it looks brighter around the edge, but it's a shell. And the white dwarf, this little object sitting right over here, is the white dwarf remnant. And after 50, 100,000 years, the shell will be so dispersed that you won't see it anymore. And all that you'll be left is this white dwarf remnant at the center. So this is the burnt out core of a star like the sun. And all it's going to do is just cool and cool and cool and cool for the rest of the universe. So this is what the interior structure of a white dwarf looks like. The white dwarf is essentially a big diamond in the sky. So if you want your boyfriend or girlfriend to give you a nice present, ask them to give you a white dwarf star because it's the biggest diamond you could ever imagine. So it's a carbon-oxygen core, largely carbon and very, very dense. And then it's surrounded by a bit of helium and a bit of hydrogen. And it's just burned out. There are no nuclear reactions going, and the carbon and the oxygen are just cooling in the center. The carbon-oxygen atoms are just cooling in the center, and that provides the heat for the white dwarf. That's why we can see it. So they're just losing energy. That energy is being radiated out into space, and that's why we can see the white dwarf. So white dwarfs are born super hot, and then they just cool very slowly over time. And we can model this process. I mean, theoreticians have spent their life modeling this process. And so we know that if a white dwarf of a given mass has a certain brightness, we know from the modeling, how long it's taken the white dwarf to reach that temperature, that brightness. And this gives us an estimate of the age of the white dwarf. So let me make that a little bit clearer in this diagram here. So here is a diagram that shows how white dwarfs cool. And again, it's the same kind of diagram we saw before. it plots basically the brightness of the white dwarf on the y-axis and basically the temperature along the x-axis. And so if, for example, if you take a white dwarf of 0.4 solar masses, after it's born, it'll cool along a track like this. It'll cool along this track. So for example, let me take this one here because I have the numbers down. This is for points, this is 0.4, 6, 8, and 1 solar mass. So here's how 0.6 solar mass stars will cool, 60% the mass of the sun. So if we find one of these with an absolute magnitude of about 14, and we know it's 0.6 solar masses, we know how old the star is, we know how long it's been cooling for, and the answer would be it's been cooling for about 2 billion years, okay? So this is an important thing. White dwarfs are good clocks. The fainter the white dwarf at a given mass, the older is the white dwarf, and this is how we can age white dwarfs. So we know the age of a white dwarf simply by how cool it is and what its temperature is. So make sure you understand that because that's going to come up a lot as we continue. Anybody have a question like this, or should I just go on? I'm happy to answer one if there's any confusion. Okay, so white dwarfs, the mass of a white dwarf is not random. It's related to what the star that it evolved from, and that's a thing called the initial final mass relationship for white dwarfs, which is an important subject. It's fundamentally important in astrophysics. So I'm going to spend quite a bit of time talking about it because it's the basis of everything that we've been working on. So what this initial final mass relationship does, it connects the mass of the white dwarf with the mass of its progenitor when it was on the main sequence. So for example, if we think of the sun here, the sun is 1 solar mass now by definition. After it evolves, it's going to make a white dwarf of perhaps half the mass of the sun. So in this case, the initial mass would have been 1 solar mass, and the final mass would have been half a solar mass. Okay, so that's the relationship that we're talking about. And it's fundamentally important in astrophysics, this, because it tells you something about the rate of supernova, the rate of formation of neutron stars. It really controls how galaxies get enriched in chemical elements and how star formation goes on in galaxies and so on. And it also turns out to be an important test of physics because we know that white dwarfs can't be arbitrarily massive. There's a limit to the mass of a white dwarf at just under 1.4 times the mass of the sun. Okay, so all of this is encompassed in this initial final mass relationship, which I'm going to talk about quite a bit in detail here now. So how do we derive this initial final mass relationship? And all we're trying to do is ask, what's the mass of the white dwarf and what's the mass of the precursor star, the star that formed this white dwarf? So here is a diagram, which you can see on the right, which is called a color magnitude diagram, similar to what we saw before. Again, it's the brightness of the star increasing on the y-axis, and basically the temperature of a star on the x-axis with hotter temperatures toward the left. So the scatter of points that you see here, this is what's called the color magnitude diagram of a star cluster. So the scattering of stars that you see here are all the stars in the star cluster. And the stars way up over here at the bright part are the stars that have just completed their nuclear evolution, and they're going off into the giant branch. And there's actually a giant star up over here, which you can see. So this star has actually completed its nuclear evolution, and it's on its way to becoming a white dwarf. Okay, these stars are just turning off. And down over here, you can see that this cluster actually has a white dwarf in it. And here it is, very low luminosity, very faint compared to the other stars, and it's quite high temperature. And these lines that you see here are these cooling models that I mentioned before, and these are 0.6, 0.8, 0.8, and 1 solar mass, right? So the cooling models tell me what the age of the white dwarf is. So this star has cooled down this much, since it was actually started it way up here and it's cooled down to here. So the cooling model tells me what the age of the white dwarf is. How long has this white dwarf been cooling for? If I subtract that age from the age of the cluster, which I get from these stars that are now turning off, it tells me how long the white dwarf has. Sorry, let me say that again. So these stars are just turning off. So I have a mass for these stars. And models will also give me an age for these stars. So let's imagine that these stars are 200 million years old. This white dwarf has been cooling, let's say, for 100 million years. If I subtract the two, it leaves 100 million years. And that tells me the main sequence lifetime of the, whoops, what happened here? That tells me the main sequence lifetime of the star that made the white dwarf. If that's not clear, it'll become a little bit clearer in just a second. I'm going to come back to that in just a second, but I just want to show you a little bit about how we know the masses of these things. What's plotted on the right are what are called spectra of a number of different stars. And some of these stars, the top star over here is a supergiant star way up over here, very luminous, hot star, about 10,000 degrees, but it's very bright. This star over here is less luminous. This one is even less luminous. And this star over here is, in fact, a white dwarf. But they all have the same temperature. That's an important point here. And you can see that the spectra are very, very different. These are quite sharp lines that you see over here. And these are very broad lines over here. So you can get a broadening of the line due to two things. You can get it due to temperature, but that isn't the case here because all these stars are the same temperature. The other way you can get a broadening of the lines is if the gravity increases in the star, and that just squishes the atoms together so they can interact more, and that broadens the spectral lines. So the very broad spectral lines that you see here in this white dwarf star are due to the fact that it's a very compressed star, and the atoms that are doing the radiating here can interact with each other quite a bit. Okay. All right. So here's a spectrum of a real white dwarf. As you can see, these are spectral lines, and from how broad these lines are, we can determine the mass of the white dwarf by fitting models to this spectrum. And on the right, you can see we fit models to the spectral lines in this white dwarf. So this tells us what the mass of the white dwarf, which in the initial final mass relationship defines what the final mass is. Okay, so the idea here is the progenitor is the initial mass, and the white dwarf tells you what the final mass is. And there's a mapping between those two. And this is what the mapping looks like. So along the y-axis is the final mass, the mass of the white dwarf. And along the x-axis is what is the initial mass of the star. So there's a real nice mapping between the initial mass and the final mass. And remember that these stars have to be in star clusters because it's the only way you can get the initial mass of the white dwarf. And I'll come back to that if it's not clear. But you can look at this diagram and see, wow, that's a really messy diagram. There's a lot of scatter in this diagram. Some stars have huge error bars. This one marked GD50 has a huge error bar. And you can draw a straight line through it here, but there's an enormous amount of scatter. And the project that we were involved in is trying to clean this up and see if there really is a strong upper limit to how massive a star can make a white dwarf. You can see that, there's a cutoff at sort of 6, but maybe there's this one star here with a huge error. And so the idea of this program that we were working on was to see if we could clean up this diagram and do a much better job. Okay, so I'm going to leave this for a moment, and I'm going to talk about something which every astronomy student hates. I hated it certainly when I was an undergrad and a grad student, and that's what's called astrometry, which is the most boring thing you could possibly imagine. It's just the idea of the position and the motions of stars and other celestial bodies. Excruciatingly dull with very complicated diagrams, but it's really turned out to be incredibly important. Okay, so just an idea what astrometry is all about. For the astronomy students, you'll know all about this. One part of astrometry is positions. What's the position of a star on the celestial sphere? And it's just measured in two coordinates. One's called right ascension, one's called declination, but you can just think of them as two angles. That's all it takes to measure the location of a star on the celestial sphere. The second one is of an important quantity in astrometry is the parallax, which is a measure of how far the star is from us. So for example, if here's a nearby star and back here are some distant stars, here's the Earth on one side of its orbit. 6 months later, it's on the other side of the orbit. When we're at A, we look along here, the star looks like it's in this position with respect to the background stars. And when it's at B, it's at this position, and it looks as though its position has moved a little bit, from here to here. And this is basically this angle that you measure over here, which is the parallax angle. And you should appreciate that if I measure this angle, and we know the Earth-Sun distance, I can solve for this triangle, and that gives me the distance to the star. And that's what parallax is all about. Okay, so it's a geometric way of getting the distances to stars, but it has tremendous limitations because this angle gets very small very quickly. And so you can't use it to measure things across the galaxy, for example. Okay, the last bit of astrometry I want to mention is just what are called proper motions, which is just a motion in the plane of the sky. I don't know anything about the distance to the object, but a star, and I'll show you a picture of that in just a moment, is just moving across the plane of the sky. And that motion measured in some angle per time is what's called proper motion. So it's a measurement of angle per time. Seconds of arc per year is the usual measurement. Here's a few measurements of what proper motions are for stars that we know and love. Barnard's star has the biggest proper motion of any star known. It moves about 10 seconds of arc per year. Our friend Sirius only moves a little over 1 second of arc per year. Some stars move very, very little, over only a hundredth, a few hundredths, a few thousandths of a second of arc per year. And a galaxy, since it's so very far away, moves this incredibly small number. This is a M33, which is a companion to the Andromeda galaxy, doesn't move very much at all. Okay, so appreciate that the proper motion depends on how fast the object is moving, but also on how far away it is, right? And the nice thing about proper motions, the longer you wait, the thing is just moving. The longer you wait, the better is going to be your proper motion measurement. So here's what proper motion really looks like. So this is Barnard's star, and this is 20 years of photography of Barnard's star with respect to a number of background stars. And so this is what the star looks like, that has the biggest proper motion of any star that we know of in our galaxy. And notice that I can measure this proper motion in some angle over per year or per decade or whatever it is, and I don't have to know the distance to the star to measure its proper motion. Okay, so that's what astrometry is all about. Astrometry is going to ruin the night sky eventually. Here's what happens. Proper motions are going to ruin the night sky after a period of time. Here's what Ursa Major looks like, the Big Dipper. That's what it looks like today. This is what it looked like 50,000 years ago, because these stars are not all moving together. In fact, this is not a cluster at all. So they all have their independent motion. So 50,000 years ago, the Big Dipper looked like this. I don't think you would have called it the Big Dipper at all. Maybe the line with a point on it or something. And 50,000 years from now, it may still look like a little bit of a Big Dipper, but you can appreciate that, 100,000 or 200,000 years from now, you're not going to be able to recognize the Big Dipper at all. So proper motions are just going to destroy the constellations as we know them. A sad, sad story. Okay, the history of astrometry astrometry is very, very interesting. It goes back to the Greeks, actually. 150 BC, Hipparchus actually measured the positions in the sky of about 1,000 stars. But he did it with his eye, and he had no instruments, and his accuracy was about 1,000 arc seconds. Not very good. All of this was pre-telescope. Telescope came in just after 1600, and you could see Tycho Brahe, who was the best astrometer of all, measured things to about 30 or 40 seconds of arc. The telescopes came in around over here, and you can see that over time then there's been a tremendous improvement in the quality of astrometry up until the Hubble Space Telescope, which is now being able to measure things with an accuracy of about 3/10,000ths of a second of arc. And the Gaia satellite, which I'm going to talk about now, can measure things to something like 1/10,000th of a second of arc, or even better. So there's been an enormous improvement, but it's taken a few thousand years. Okay, so this is Gaia. I don't know, have people heard about Gaia? No? Eleanor, is Gaia something you've heard about or not?
I've heard some of it. We haven't talked about it in a whole lot of detail.
Okay.
But I am at least somewhat familiar with it.
Pauline knows all about it. I can see that. Okay, so this is Gaia. This is an astrometric satellite. Not the first of its kind, but by far the best of its kind. It was launched in 2013 by the European Space Agency, and it went out to what's called L2. L2 is out over here. It's what's called the Lagrangian point. It's a stable point of the Earth-Sun system. In other words, if you put a satellite out at L2, it sits there. So as the Earth goes around the sun, it drags the satellite with it. And if you just look out over the time of over a year, you'll be able to observe the whole sky because the Earth has made one orbit around the sun, and the satellite at L2 basically follows the Earth around the sun. And it doesn't move, by the way. It stays at that Lagrangian point. It's about 1.5 million kilometers beyond the Earth. The James Webb Space Telescope, which is going to be launched within a year, is going to go to L2 and so on. So it's a very important point for looking out at the sky. So Gaia works something like this. So here's the satellite, and it has two lines of sight. A camera looks out in this direction, and it looks out in that direction, and it's actually spinning very slowly. So these two lines of sight will track a portion of the sky in a 6-hour period. And they'll measure positions of every star that they see. But at the same time, the Gaia axis is actually precessing around the sun like this in 63 days. And remember that the whole thing is moving around the sun. So you can anticipate that over a period of a year, you're going to map every point in the sky many, many times. In fact, as each point in the sky will be mapped about 70 times over the Gaia lifetime. And that's why it's getting this incredible accuracy. So here's what Gaia gives us. It gives us 5 little bits of astrometry. It gives us the positions of the stars. It gives us the proper motions in these orthogonal directions, and it gives us the parallax. And it has done this for 1.3 billion stars. There's a big catalog that's been published already. And that's the catalog that we exploited, which I'll be talking about in a few moments. Early data release 3, believe it or not, came out yesterday from Gaia. And if you want to know how aggressive astronomers are, there were 10 papers published yesterday on the data that came out yesterday. So these are people that really jumped on things. It's an incredible thing. I wouldn't have believed it. Okay, so here's what Gaia does for us. For stars that are 20th magnitude, these are quite faint stars for Gaia. Gaia's limit is probably maybe only a magnitude fainter than this. Here's the idea of what the accuracy is. But if you want to get a real good idea, just think of the bright stars. It can measure the positions to 8 micro arc seconds on the sky, micro arc seconds, okay? It can measure the proper motions to 5 micro arc seconds per year. And for the faint stars, it's about 300. And the parallaxes are, for bright stars, are at 5 micro arc seconds accuracy. So that's 0.05 parsecs, 0.05 parsecs at 100 parsecs. So it's 0.05% accuracy for a star at 100 parsecs. So this has been an incredible advancement, and we now have all this wonderful astrometric data. The catalog was published with 1.3 billion stars in it. You know, that's like a few percent of all the stars in the galaxy. So it's an incredible achievement. It was made public to everybody, and there's been thousands and thousands of papers that have been published based on Gaia data. The estimate is that 5 a day get published on Gaia data. So it's been an incredible rich data source. Okay, so we use this to try and find, I'm going to try and bring everything together now. So we use Gaia to try and look for very massive white dwarfs in star clusters. And remember, we want them, they have to be in star clusters because that's the only way we know what the precursor mass was. And I'll come back to this in case you've forgotten about that. So what we did in this survey, we surveyed all star clusters that basically are young, 10 million years up to 300 million years, and distances less than 1.5 kiloparsecs. And the white dwarf candidates in the cluster, they had to pass very stringent tests, which I'll show you in just a moment, astrometry tests. And so we surveyed just under 400 clusters to try and find very massive white dwarfs and clean up that initial final mass relationship. So this is what the survey looked like. What's plotted here is the distance to the cluster going from 0 up to 1,500 parsecs. Everybody know what a parsec is, by the way? Parsec is a unit of distance. It's about 3¼ light years. A light year is the distance light travels in a year. It's a couple of trillion kilometers. Okay, so this is the distance in parsecs, and this is the log of the age of the cluster. So this is 100 million years at 10 to the 8. And we surveyed all these clusters here, all young clusters out to about 1,500 parsecs. So this is an image of one of the clusters that we looked at. The one on the left is an image you can get. It's Messier 47. It's a bright, well-known cluster. It's a picture I got off the web somewhere. The picture on the right you should be more interested in. This is the one which we took with the UBC Southern Telescope. I don't know if you knew that UBC has a Southern Telescope, but we have a Southern Telescope, and it's in the process of being replaced with a half-meter telescope in a very good site. It's on Cerro Tololo, which is one of the great sites in the world. It's a new telescope. We've been caught up in COVID and it's not installed yet. In fact, it's sitting in the basement of the Hebb building at the moment, but it'll be shipped down to Chile as soon as COVID allows us to do that. And you as students will have access to this thing. Hopefully you don't graduate before it gets installed. But this is a picture we took with the precursor telescope to that. We had a smaller telescope and not as good. And that's what, I don't know, a 2-minute exposure with a decent telescope and a decent site looks like. So it's going to be quite an impressive little telescope. Okay, so how do we find these white dwarfs and what do we do with them and so on? So this is you can look at the left-hand one here is fine. So this is, we're looking out at the sky and it's about a 4-degree diameter field, okay? This is not a picture, but this is what the proper motions from Gaia look like of all the stars in that field. So it's a big piece of the sky, 4 degrees diameter, which is a pretty big piece of sky. And you can see that there's this big, huge blob here. which has about 500,000 stars in it. So these are stars that are in the disk of the galaxy, in the Milky Way. Okay, and they have pretty much the same proper motion because the whole galaxy is moving around together. But there's somewhat of a spread. So that's what this big blobby thing is over here. Remember, this is not an image on the sky. This is just a 4-degree diameter field, and the proper motions, the motion in right ascension in this direction versus the motion in declination. So you can see that the stars in the galaxy are moving more or less together, but there's some scatter. But you can see on top of this that there's two concentrations. And these are what star clusters look like, right? They're a small group of stars that are basically moving together because they form together. They're moving together, and they're moving somewhat differently than the rest of the disk of the galaxy. And this is how we pick out the star clusters that we're interested in. Okay, and then we continue with that. We pick them out in proper motion. We measure all the parallaxes of the stars from Gaia in that region. We keep only those that are within 2 sigma of the mean. This is within 2 sigma of the proper motion. And this is the distribution on the sky. So this is what we define as a cluster. We've picked out that big grouping, and we've selected out of that dense little cluster the ones that have the same parallaxes and are at the same position in the sky. And this is an example of quite a wimpy star cluster, but it's got the most interesting white dwarf we discovered. And you can see that the cluster itself is very wimpy. It's just some few stars that you can see up over here. Okay, so here's how we do the things that we want in terms of getting the initial and final masses. So here's the color magnitude diagram of the star cluster. So all of these dots are individual stars in the cluster, and you can see that the stars are just turning off over here. That allows us to date the star cluster, and this particular one is about 90 million years old. You will notice down over here there's a faint white dwarf. So this is the white dwarf we discovered in this cluster. Now, we know from these models that the turn-off mass, the stars that are just moving into the giant branch, are about 5.6 solar masses. We know that from models. We know that the temperature of the white dwarf is very, very hot. It's more than 100,000 degrees. And we can measure its mass from its spectrum. Not a very impressive spectrum. And why is this? Someone tell me, why is this spectrum not very impressive? The lines are not very deep. They're not very strong. So what is it that makes the lines not very deep and not very strong? If it's very hot and it's very high gravity, that really broadens the line. And that's why you can barely see the spectral lines here in this plot and in this plot, because the star is so hot and it's a very massive white dwarf. Okay, so from the white dwarf cooling, we know that this white dwarf has been cooling for only about 250,000 years. It's incredibly hot. And basically it was formed yesterday. So the precursor mass of this thing is pretty much the same as the turnoff mass. Is that a point that people understand? I hope. Right? Because it's been cooling for no time at all. So it's basically zero. It's been cooling for zero. So its precursor mass is the same as the turnoff mass. So its precursor mass is 5.6 solar masses. Okay, I have to get out here and then come back in. So I have to unshare my screen because I want to show you a pretty picture. Let me see if this will work. I hope this will work. Let me see. All right, I think it might work. All right, so here's a blow up of that cluster that has that very hot and very young white dwarf. And I'm going to zoom in I hope this works and it doesn't go crazy on me. There is 114,000 degree white dwarf that was born yesterday. And this is the coolest white dwarf that we've discovered in that cluster. So that's
the picture isn't showing up. We're still just seeing the slide.
The picture doesn't show up?
We're just the link.
Oh. Okay, let me. So, okay, so you now see my screen?
Yes.
With graphs and stuff, right?
Mm-hmm.
Okay, let me see if this will work. Maybe this will work by itself. Does the picture show up now?
No, it's still just, that's weird. Why is that happening?
I don't know.
You might have to do a new share and choose your browser.
Let me okay, still not?
No. Oh, now I see it.
Okay, so that's the image. Okay, so I'm going to zoom in. So that's what 115,000 degree white dwarf that was formed yesterday looked like. It's about the bluest thing you could ever imagine as a star. It's an incredible object, and we were so delighted to find it. Okay, I'm going to have to get out of here. Now that I'm here, I can't get out. Okay, I'll have to share my screen again, I think. Okay, do you see that now? Are we?
Yep.
Okay, all right, let me just show you quickly one other white dwarf that we discovered, and then I think we're getting on in time. So I'll try and end in a few minutes. Here's another one. It's a much older cluster, 280 million years. We know that from the stars that are just going off into the giant branch. The turnoff mass is just under 4 solar masses. The white dwarf, here's the white dwarf down over here in the color magnitude diagram, faint in blue. Here's the spectrum, and here's the analysis of the spectrum. We know that the mass is just under 1 solar mass. It's been cooling for 175 million years. So if I subtract this number from 280 million years, I get 105 million years. And so then I ask the question, what's the mass of the star that lasts for 105 million years on the main sequence? And it turns out it's 5.4 solar masses, which is the precursor mass to this particular white dwarf. And here's just a whole bunch of spectra, not interesting, not too interesting. Okay, so here's the diagram which I showed you before. In the end, we discovered 6 new massive white dwarfs in these clusters. And we went through with Gaia and we checked every star in this diagram and to see if it really was a member of the cluster, because this is all pre-Gaia. And we found that most of these were not in Gaia and are probably not cluster members. So this is what our new initial final mass relationship looks like. Instead of this, we now have this. And this is checking every star, whether it was in Gaia, in the star cluster, and it was a member of the star cluster. And it's the same data, it's the same plot, the final mass along the x-axis and along the y-axis, and along the x-axis, the initial mass of the star. And all the ones in red are the new ones that we discovered. So this is a relationship which is now very, very much tighter than the previous one. And there's an enormous amount we can do with this. So one of the things that we found, as I said, all the ones in red are the 6 new massive white dwarfs that we found in clusters. And you can see they're among the most massive white dwarfs known in star clusters. 2 things were a little disappointing. We didn't find very massive white dwarfs, nothing more than about 1.1 times the mass of the sun. Remember that white dwarfs can go up to the end of the y-axis here. So this is what's thought to be the limit for white dwarf masses at just under 1.4 solar masses. And we didn't find anything anywhere near that massive. The other thing is that we didn't find precursors that were more massive than about 6 solar mass. So 6 solar mass seems to be about the main sequence mass limit for white dwarf production. So it seems from this, if we're right, that stars of 7, 8, 9 solar masses do not make white dwarfs, but may make supernovae instead. And that really causes an issue with the supernova rate. This predicts that there would be too many supernova, and we're not sure what the implications of that are at the moment. Okay, a couple of quick slides and then we'll stop. I praise Gaia. Gaia has been an amazing boon to astronomy, even though it just does astrometry, but it's been fantastic. But Gaia has limitations. It's no good for very faint stars, and it's not very good for stars in very crowded regions. And so we're going to continue to use the Hubble Space Telescope and the James Webb Space Telescope if you want to probe really dense or faint environments. And just to show you that, here's this is an image we took maybe 7 or 8 years ago with the Hubble Space Telescope in the center of a bright globular cluster. And you can see that we've resolved the stars completely right into the center of the cluster. I made a picture from the Gaia data of the same field, and it looks like this. And you can see what happens. You know, it's just is way too crowded in the core for Gaia. So if you want faint or you want very crowded, Gaia is not the thing for you. Okay, I want to finish with this because these are 2 star clusters that were in our survey for which we found a number of white dwarfs. 1 white dwarf in the Pleiades and half a dozen in the Hyades. But I just want to impress upon you what we're really looking at when we talk about these star clusters. Number 1, they are very pretty. These are beautiful objects in the sky. The Pleiades, very young, you can see it with your naked eye. The Hyades, you can also see it with your naked eye. They're only about 20, 25 degrees apart on the sky. But the other thing I want you to appreciate is that these are very dirty environments. There's lots of dust, which causes some stars to be made fainter than other ones. And one of the things we have to sort out all the time is, you know, are stars in the cluster being made, some of them being made fainter than other stars? We have to correct for that. And so it's a little bit more complicated thing than you might have imagined. But here's a beautiful example of 2 of the star clusters that we looked at, very photogenic and very pretty objects to look, even with your naked eye. And I think I'll stop there.
Kind of awkward when no one else has their mics on, but
Okay, we're not at 6 o'clock yet. Good. I'll be happy to answer some questions if there are some.
yeah, anyone feel free to.
You can just unmute and ask. You don't have to throw it in the chat or anything.
Pauline here. Is it possible to do any kind of this type of measurement for white dwarfs that are found in planetary nebulas?
Not entirely, because if I find a white dwarf in a planetary nebula, I don't know what the precursor mass was. I can measure the white dwarf and I see some shell of gas around, but I really don't know what the mass of the precursor was. So I can't put those stars in this initial final mass relationship. I mean, they'll have other purposes, which are very interesting. Planetary nebulae are fascinating things to work at, but they're not objects which we can put in the initial final mass relationship unless I know what the initial mass was. And looking at a planetary nebula, I just don't know that. And remember that, you know, if I if I find a white dwarf sitting in the disk of the galaxy, I can measure its mass and everything, but I can't put it in the initial final mass relationship because I have to know what its history is, right? What the star cluster it came from, and in that way I can get it its initial mass, and I can't do that unless it's in a star cluster. So that's why we've just concentrated on working in star clusters.
That's fascinating that you can actually figure out the initial mass. I'm sure
Yes,
lead to many more discoveries.
And it's due to you know, a number of people doing over decades and decades doing wonderful models. We need a cooling model for white dwarf. We need an evolutionary model for a main sequence star. And this is a lot of people doing a lot of very complicated physics to figure all that out. We're the beneficiaries of it. Thank you, Colleen. That was a very nice question.
I was just wondering for like the models that we can construct for like the diagram with the main sequence, and there's a model for different masses. So do stars with the same mass all kind of cool at the same rate? Is that why we can?
Yes, so white dwarfs of the same mass cool at the same rate. So a white dwarf at 0.6 solar masses in this cluster is going to cool at the same rate, we believe, as a white dwarf of 0.6 solar masses in some other cluster, right? So things get a little messier when you get very high mass, because that might depend a little bit on the core composition, whether exactly what chemicals are in the core. So there might be a slight difference there. But in lower mass white dwarfs, they all cool at the same rate. Of a given mass, they'll all cool at the same rate. And the other thing is, for stars that evolve off the main sequence, again, if they all have the same composition, I mean, a 1 solar mass star in this cluster will spend the same time on the main sequence as a 1 solar mass star in this other cluster. Astronomy would be very chaotic and very difficult if that were not the case. Then we wouldn't have anything to really work with if everything was just on its own and they didn't all have the same kind of thing. So it's very good that it does.
I see. Thanks. I think someone asked a question in the chat.
I have to get my glasses out.
It says, do you think you just haven't discovered white dwarfs bigger than 6 solar masses, or they don't exist?
So that's from FIFA. FIFA, that's a super good question. Okay, here's the story. We looked around rather small area around these clusters. But we know for a fact that, you know, given how many stars there are in a cluster, we know that in some way we are missing white dwarfs. In fact, as we're missing a lot of white dwarfs in these clusters. We were surprised we only found 6, and we observed 400 clusters and we only found 2 new white dwarfs, which is really quite a bit of a shock. So we've actually done another search, which is a much wider area search, and we're finding more white dwarfs. So here's what we think is happening. And that argues a little bit about what I said earlier. We think that white dwarfs are getting kicked out of clusters. sort of like your brother, you know, who's not acting very well and he gets kicked out of the house, right? So he's not in the house anymore. And that's what happens, we think, to some massive white dwarfs. How do they get kicked out? Well, remember that that white dwarfs lose mass, and maybe the mass isn't symmetric. Maybe there's a little bit more off in one direction, maybe because of rotation or something else. There's a little bit more in one direction than there is in another direction. That'll act like a jet, and the white dwarf will move in the opposite direction where the mass is being ejected. And that could give it a velocity. And even if the velocity is pretty small, 1 or 2 or 3 kilometers per second, these clusters are 100 million years old. And over 100 million years old, 1 kilometer per second is a very large distance. And they could have escaped from the clusters. So we think that that's a real possibility here. And so the upper limit that we're finding may not be the real answer, because very massive white dwarfs are being kicked out of clusters. Now, FIFA, the other thing about this is, if you go out and you look not in clusters, let's forget about clusters, you just look in the field of the galaxy and you find white dwarfs, you do find white dwarfs that are more massive than the ones we've been finding. You do find ones that are 1.2, 125, 1.3, which could be the missing massive white dwarfs that we're not finding. The problem is we don't know what the history of a white dwarf is. White dwarfs, if they formed in clusters, they could be in binary stars, they could have merged, and you have a 1.3 solar mass white dwarf because a 0.6 and a 0.7 solar mass white dwarf merged. So that's another thing that we have to keep in mind. When we look at the ones in clusters, we can generally tell, you know, what if it's had a clean history, because if its age is less, its cooling age is less than the age of the cluster, and it all makes sense with the initial final mass relationship. But a white dwarf sitting in the field, which looks as though it's very massive, we don't know what its history is, and it could be a merger or even a triple system. And again, that's another reason why we just stick in clusters with white dwarfs that are very clean, and we know what the history is. They have a clean history. So things can get quite complicated. All right, Eleanor, are we done?
I think we might be. Last call for any questions? Anyone?
Okay, it's last call because it's first call for the bar now.
Okay, ending recording.